This is 12/17/2010, 2:12 a.m. This is for UMass Lowell's Electronic Engineering Technology, Project Laboratory A. I have built a rotary encoder pulse counter. This device, the rotary encoder, is used on servo axes on the machine tools that I work with on a daily basis. I needed a way of counting the pulses on these things so that I wouldn't have to throw them out or have them rebuilt. So this device here, it's supposed to put out a certain number of pulses for a certain amount of radial displacement, so the machine knows how many revolutions it has gone. I built this piece of hardware out of about $20 worth of material, including some old 7-segment LEDs that date back to the mid-80s. There's a PIC microcontroller, a filtering circuit. The PIC is outputting to some transistors and that power each one of the displays individually. And they turn on and off really fast so that they look like they're concurrently on. I wrote a number of codes, all in C, using the microchip MPLAB IDE. The first program is segment test. All it does is map out, it goes over and looks at each segment, lights them up one at a time to make sure they're all working and to make sure I have the pins and wires all mapped out the right way, which I did eventually. The next program was FFF-display-test.c, which uses those 3 displays to count from 0 to FFF and hex and display the hexadecimal characters appropriately. This proves that my bit mapping for those hex characters and the algorithm used to split the big number into little numbers for each individual display works. The next one is external oscillator, which I used to get the timer counting from an external clock source, which in this case is the pulses from the rotary encoder. That took some getting used to. Once I got that, I got it to count and display the number that it was getting from the rotary encoder. It would just continually display it in a big loop. And then for the final one, this program, count display final.c, it has a number of subroutines, but basically in the main loop down there, it loops while it's in display mode, it loops and displays the current number of memory until an interrupt is seen, which brings it back and turns the timer, either toggles the timer on and off, reads the new number from memory and loads it, sends it back into timer mode or display mode. The external interrupt is generated by the marker pulse on the rotary encoder, which goes off once per revolution. So when it sees that marker pulse, it starts counting, and when it sees it again, it stops counting and goes into display mode, and it continues to display the hex number, the value of the number of pulses, until it sees another marker pulse. The device itself, just to see that it's working here, right now the way it's set up, it cycles through the hex number that it collects. It's cycling through on one display. Let's just watch this thing work here. I rotate this from 1 until it sees a marker pulse, and then once more around. That's the marker pulse. I'll go around one more time. There. And now I'll get a new number, 0D4, that's not it, 30D4, which turns out to be, in hex, 30D4 is 12,500, which it's kind of hard to see in the camera, but that's 12,500 pulses that it's seeing. And I can prove that it's actually counting by bringing it back into count mode, moving it past the marker pulse, and then moving it back and forth a few times, and then bringing it past the marker pulse again, and then we should get a new number. 4D C2, and if we go over here, 4D C2 is 19,906. That's because I added some pulses going back and forth. So a number of compromises were made in the hardware here. This ends up only really being a proof of concept. Originally I wanted 4 displays so I could display a 4-digit number for 1200 pulses. And then I realized that I ran out of pins on my microcontroller. So I used 3 7-segment LED displays and was going to put display the number in hexadecimal. That works great. But then I realized that actually I need 12,500 and I don't have enough pins for that. So I have the 4-digit hexadecimal number just cycling through one of the displays right now. Another problem I had is that one 9-volt battery is not enough to run this large encoder and drive the microprocessor. The encoder, or the microprocessor, really wants to see a strong 5-volt pulse, which means the encoder needs to be well above 5-volt input. So 9 volts would be great, except the battery, when you plug it in, it just drains down really fast. So I have the whole thing powered right now by a power supply running at a solid 9 volts. It draws about 150 milliamps. So the next revision will be probably powered off of an AC to DC converter, something you can plug into the wall, and it'll have probably a larger PIC that I can plug 5 7-segment LEDs displays into, so it's more user friendly. And also these LEDs here, one will light up when the power's on, one will light up whenever it sees a marker pulse, so that you won't have to strain to see the line that's drawn in the shaft here. Let me go ahead and see this count one more time. There we go. See what our new value is here. 30D4, and that is 12,500. So it does actually work. This has been a good project. I've built a useful tool. I've learned how to use the PIC microcontroller and its timer function. It's external, using its external clock. I've figured out how to make this a more user-friendly device, which I will be doing in the next revision, and we will be using this on a regular basis. And that's it.